Hello there, and welcome to a little video segment here. This will probably be the first one that you'll see of me demonstrating how Gauss's law is actually used for something practical. Now you got to realize that practical in physics doesn't exactly always equate to practical in everyday life, but I think this is probably the most basic application of Gauss's law, one that you'll certainly find in your textbook and most textbooks. And what we're going to do with this is to take a situation that we saw before in the Coulomb's law chapter, and that is a hollow metal shell, and use Gauss's law this time to describe what we previously described using Coulomb's law, which is like the fundamental law that describes the interaction between charges, and also Newton's shell theorems, which describes perfectly what's going to happen both inside and outside this shell. So you'll see me drawing things by hand because I think that's the best way for you to see how to do it yourself. I am going to use different colors, and I'm going to encourage you maybe to have a couple different colors around, because by the time you draw all this stuff on the diagrams, it can really look awfully cluttered. So let's just start with basic black here. I'm going to draw the hollow shell and just use a nice little circle there. And then I'm going to give this shell a little bit of thickness. And so that'll represent the hollow cavity inside. Now, as you can see, that that's not perfectly drawn. It's not perfectly symmetrical. I do have little tricks here on the screen that I can use to move things around. You don't really have those kinds of tricks, and so I'm not going to employ too many of those. That way you don't feel like I'm doing anything that you're not able to do yourself. So there's a picture of what the shell might look like. I'm going to assign to this shell some charge. And I'm going to be careful how I'm using my symbols here, because it's not a great practice to use symbols for a particular situation that are also used commonly as just symbols in generic equations. So what I'm going to do in this case is I'm going to assign a positive charge to this by writing positive Q, and then I'm going to use the subscript shell, and that'll designate this particular charge on the shell. It's not a very small subscript, but I want you to be able to see it, certainly. The last thing I'm going to do is I'm going to mark a couple of points on here that I'd like to use to describe what we know about the electric field. So I think an obvious point might be a point, we'll call it P here, at the center. Another point here in the hollow part, but not at the center, I'll call that P sub H. A point P that's here actually in the inside of the metal, the thickness of metal itself. And then a P somewhere outside, I'll call that out. So we've got 4 different points marked there. The center, everywhere else inside the hollow cavity, inside the metal itself, and then somewhere outside the entire shell. Now, the first thing you want to do before you start trying to employ Gauss's law is to ask yourself whether it is appropriate to the situation. And by appropriate, really the key question is, do we have symmetry? There are basically 3 kinds of symmetry that we look for in a problem like this. This one is known as spherical symmetry. So in this case, the answer is yes. Now, if we had something like an oblong shape, like an egg-shaped shell, then the answer would be no. And we would completely abandon any attempt at using Gauss's law. The other kinds of symmetry we might look for are linear or cylindrical symmetry, as well as planar symmetry. And again, those are described in your textbook and all good college-level physics texts. So now that we know we have spherical symmetry, we've got to imagine that that positive charge that we drew on there is really evenly distributed spherically around the entire surface. Now, you ought to know at this point exactly where on that metal that charge is located, but I'm going to actually show you how we use Gauss's law to demonstrate that that must be the case. So we'll come back to that in just a moment. The first question we might want to ask is, well, what is the electric field at the very center, that point that I marked P sub C? And I'm choosing that one because I don't think we really need to use any tricks at all to describe that. simply appeal to symmetry and say, well, if that charge is uniformly distributed around the entire shell, then every charge on one side, let's say the right side of the shell, has a charge directly opposite it on the left side, creating the exact same electric field contribution in the center. And so every piece has something that cancels it out. And we used Coulomb's law before to demonstrate the same thing. Now, what do we do about that point there in the hollow part? Well, here's where I'm going to demonstrate actually what it means to use Gauss's law. So I'm going to take a color. Here, I'm going to use green, and I'm going to encourage you to use a different color as well. And we need to draw at that location an imaginary Gaussian surface that matches the symmetry that we're using here. Now, we're using spherical symmetry, and a Gaussian surface is just an imaginary surface. You can draw it dashed so that you remember there's nothing really physically there like there is here on the shell, but it's just something that we can picture, and it's a whole lot easier to picture it if we can actually draw it. So there it is. Now, I'm using a two-dimensional screen here, so it doesn't look very three-dimensional, but you have to picture that as just a three-dimensional spherical shell, and I got the shell's surface to coincide with that point that I was interested in. And now we have to talk the language of Gauss's law. We would say, okay, if there was an electric field at that location, would the electric field be the same everywhere at different points around that Gaussian surface? And again, we're appealing to symmetry here, and we would say, well, you know, if I was there at that little point marked piece of H, would it really feel any different to me if I were at a different point, let's say over here, or anywhere? I mean, if you were actually walking along that imaginary place, you probably really couldn't tell where you were on that sphere because every point on the sphere kind of looks the same as every other point. So the answer would be yes. An electric field value at one point on that green imaginary surface would be the same as any other point. So what we do is we write Gauss's law, and we're going to use that electric field value as part of our Gauss's law equation. Now here's what it means to write Gauss's law. We literally write the integral, and you put a little circle inside of it, of E dot dA. That's how we describe that. The integral of E dot dA is equal to the charge inside divided by a constant known as the permittivity constant, epsilon sub naught. Now this is a rather cryptic thing here, so I'm going to go through one part at a time. I think you know what epsilon sub naught stands for, but I'll talk about the other symbols here because if it's the first time you're seeing them, it can look awfully confusing. That E, first of all, is what I was just describing a moment ago. That is the electric field that we're trying to describe at this particular point, which I've named piece of H. Now get over the fact that we're going to find in a moment that there is no such field. We're going to imagine that maybe there is a field there, and we're going to figure out what it is. But remember, whatever that is, it's going to be the same everywhere on the entire surface. So that electric field has a magnitude and it has a direction, which is why we've indicated it as a vector. And now we're going to multiply that in the form of a dot product by another vector, a little dA vector. Now a dA vector represents a tiny little piece of area. That's what the D means. An infinitesimally small piece of area somewhere on that green surface that we've drawn, that imaginary Gaussian surface. So if there's an electric field value at that particular point, and then we've got this tiny little piece of area that we can measure at that point, both of them have directions, and we can multiply those vectors together. Now, if we do that over the entire surface area and sum all of them together, that's what we're indicating by the integral sign with the circle around it. It's called a closed integral. It means we have the entire closed sphere that we have to remember. You can't do just part of the sphere. You can't do 3/4 of it or 99% of it. You have to do the entire thing. So that's what that symbol there in the front means. Now on the other side, we have Q sub n. In refers to inside that green imaginary surface. Anything outside of it doesn't count, only the part that's inside of it. And as I said before, you know what epsilon sub naught is. It's just a value that you can plug in as a number, but we'll be keeping it here as a symbol. Now watch how the trick using Gauss's law makes life wonderful for us. First of all, notice that because E is the same everywhere on that green surface, that every time we imagine going around and multiplying that E times the little area, we're going to be using the same number every time. So that means E isn't really a variable, it's really just a value, a constant value in this case. So I'm going to make life easier by pulling that outside of the integral. The other thing I'm going to do is get rid of the dot product. Because of the symmetry we have here, if there were an electric field, it would either radiate out away from the center or radiate in towards the center, one or the other. There's no reason to think with spherical symmetry that it wouldn't be one of those. And so, because the area vector also is radially away, out from that center, then the dot product is unnecessary because these vectors are already going to be parallel to each other. And when there's complete parallelness, you can just multiply like you're used to from elementary school and not have to worry about direction stuff. And so now I can just write this as the surface area, integral of all of these little areas. I've gotten rid of my dot, I've gotten rid of my vector symbols. And for now, I'm going to write Qn over epsilon sub naught again. A little more space here. Now, I'm going to talk about what this part here means. This means the sum of all of those little pieces of area over the entire surface area of the sphere. Well, all we mean there is the surface area of a sphere, which is 4 pi times the distance squared. So I'm going to use 4 pi, and I'm going to use a symbol here, r. And I ought to define r. R is this distance out to where I've drawn my Gaussian sphere. So there's r. Okay, now here comes the wonderful trick. How much charge is inside of that sphere? Now I know there's charge on the shell, but notice my green sphere is within that. So I have absolutely none. So I can put a big 0 right there. And I don't even really need to put the rest of it, but I'm going to. Now what does this mean? Well, we know that r can't be 0, and 4 pi and epsilon sub naught aren't going to be 0. So the only thing we can conclude here, hope this isn't too much of a leap, is that the electric field at that point must be 0. Now I said going into it that we had to assume that maybe there was an electric field, and we had to talk about what direction it would go, radially out or in. But in the end, we find that there is no electric field there, and that is completely consistent with Newton's shell theorem. Okay, let's talk about point M. Where's the electric field at that location? Well, I'm not going to employ Gauss's law here. I'm going to employ nothing but logic and say that because this is a metal, and metals are filled with free to move electrons. They're called valence electrons, the conduction electrons, if you will, and they're free to move whenever something wants them to move. And the thing that causes electrons to move is known as an electric field. Therefore, if there were an electric field inside that piece of metal, we would have electrons moving. And if we had electrons moving, then we really don't have electrostatics at all. And so the entire argument is kind of a moot point. What this means is, if we're dealing with electrostatics, electrostatics implies that there's no charges moving. And so if we give this metal shell long enough, if we throw some charge on there, they will very quickly find their spots where they want to go, and they will stay put. And we will never have an electric field inside of a metal in an electrostatics problem. So therefore, we can simply say, from logic, and almost definition, that the electric field at that point is also 0. So we've done 3 out of our 4 points. And really the only one we've needed to use anything other than logic was that point there, H, that I spent all the time on using Gauss's law. So now let's do this last point. I think I'm just going to get it started for you and see if you can take it from here. Suppose we're some distance out here to that farthest point P. And let me just define that distance. Here again, I'm going to use another color. This distance out to this location here, we'll call that R sub O, because I called that point the outer point. So I'll use O for outer point. What is the electric field at that particular position there? So far, everything we've seen has been 0. Well, I'm going to tell you this one is not going to end up being 0. So we're going to use Gauss's law again, first by noticing that we have enough symmetry here to believe that at that point there, the electric field will be the same as it would at any other point the same distance away. So if I can imagine moving this point over to here, as long as it was the same distance away, or maybe over to here, and of course I can only move it two-dimensionally because of my screen, but you can imagine moving it outward or inwards. As long as it was the same radial distance away, the electric field should be the same magnitude, the same inward or outward direction, kind of using that same symmetry. And so we're going to use Gauss's law again. And we're going to draw a Gaussian surface. And I'm going to represent it by this dashed circle, trying to keep it pretty concentric with the rest. Again, yours doesn't have to be perfect any more than mine is. And we're going to talk about the electric field at any point on that big Gaussian surface that we just drew. So what will we know about it? Well, certainly it's the same everywhere as we were just talking about, and it would be either outward or inward. Now notice, because it's a positive charge I put on that shell, and you ought to know enough to know that electric fields radiate away from positive charges, it makes sense that the electric field would be radiating away here. So if I were to draw this, perhaps I'll draw it in blue at this particular point. I'll represent that as the electric field at that point, and I could draw something similar at any point on that. So now we're going to write Gauss's law again. I want to encourage you, anytime you're asked to use Gauss's law for something, you always actually write it. So I've got a little white space here. I'm going to use this to find this point P and the electric field there. So we write the integral of E dot dA is equal to the charge inside divided by epsilon sub naught. Make sure I don't get things in the way here. Move that over. And using the same arguments of symmetry that we used before, we'll say, okay, do I really need to keep E inside the integral? Well, no, because you only keep things in an integral if it's going to be different for every piece that you're adding up. And every piece of area on that sphere should have the same electric field. If I were to take a little test charge there and imagine walking around the outside of that imaginary Gaussian sphere, I would measure the same electric field. That I'd feel the same pull on a test charge or push on a test charge, depending on how you're holding it. And so I can pull that out, and I can also get rid of the dot product because, again, the area vector would be in the exact same direction that the E vector here is. And so I can now write this as E times the sum of all the little pieces of area around that sphere, which is 4 pi times R sub O squared. Let me fix that square, came out a little ugly. R sub O squared. And that's equal to the total charge inside that Gaussian sphere. Again, in refers to anywhere within what we drew as the Gaussian sphere, and that's why I always want you to draw those, like I drew in green. Well, what is that? Well, that's what I designated earlier as my Q sub shell. And that's just a parameter given in this particular instance. And so, get a little more space here just to finish up, and all that's really left to do is a little division. Notice I don't have zeros in this case. This is the one case out of the 4 where I don't end up with 0. I'm just going to solve for E. And I'm going to get, not writing it in red this time, the charge on the shell divided by 4 pi epsilon sub naught r sub O squared. And that is the electric field at position P sub O, just to be clear here. Put a box around that. It's like final expression. And I want you to notice something here. This is completely consistent with what we described before in a previous chapter using Newton's shell theorem. Newton's shell theorem said that as long as you were anywhere outside the shell, that you could treat all of that charge as being concentrated at the center. So in that case, we could say that all the charge was the same distance away, r sub O in this case. And the only difference between maybe what we see here and what you've seen in the past is we've used K in the past, the electrostatic constant, in place of 1 over 4 pi epsilon sub naught. So that is equivalent to K times the charge on the shell divided by the distance from the center squared. And it's a very important consistency I want you to see, because Gauss's law, I'm asking you to take a little bit of this on faith, because, you know, Gauss was a pretty smart guy, and I trust him that he came up with something that works, but without some good proof, I don't know why you should necessarily buy it. So the fact that it's consistent with what we know from Coulomb's law maybe is just a little bit of additional trust in what we get here. So there's a great example of a typical shell problem. There are more complicated ones than this one that we might look at too, but I think this is a good starting point for you. You'll see the same demonstration in your textbook if you look. Hopefully you'll see that the similarities between them. And I think that's going to do it for now.